All right, so good afternoon. Here we are again for another portion of the lecture number 4 for ENGR 2302, Engineering Dynamics. So I'm just going to continue right where we left off. This time I think I'll work with some numeric examples here, or some examples with numbers in them that we can work through. So let's see. Let us look at something like this. I'm going to have a 200-pound block, so this is given. I have a 200-pound block on flat surface, on a flat surface, and a force P is applied. Force P is applied at 30 degrees. And I will draw this out. And so I have my surface here. Let's see. So I'm going to have my surface, and on this is going to be the block. So I have my block on this surface. It's a perfectly horizontal surface, as you can tell from the perfectly horizontal line I drew. And there's a big block of whatever. It's got to be something heavy, though, because this thing does weigh 200 pounds. It does weigh 200 pounds. And there's going to be a force P here, and this thing is going to be applied at an angle of 30 degrees. I'm also told that there is a coefficient of kinetic friction between the block and the surface, and this coefficient of kinetic friction, the mu kinetic, is going to be 0.25. Remember this stuff from physics? Joy. Okay, so what I wish to find, though, is I wish to find the force P. Find force P. Find force P required, if I can manage to write the word required, to accelerate the block. At 10 feet per second squared. 10 feet per second squared. Okay, so we have that, and then, so jot that down. But the basic idea, the strategy I'm going to solve is, first I'm going to resolve the equation for motion into two rectangular components, and then I'm going to solve for the unknown forces and find the resulting force needed to produce the desired acceleration in the system. But the very first thing I'm going to do is to draw the force and kinetic diagrams. So let me draw the free body diagram and then the kinetic diagram. Free body diagram and kinetic diagram.
Will we draw both for every problem?
I would recommend, at least when it's applicable, yes, I would recommend drawing both for every problem as you're working through these. So if I have this here, I'm just going to draw the block twice for the free body diagram and the kinetic diagram. And let me label all the forces on here. I'm going to have P at an angle of 30 degrees. That's up 30 degrees. 30 degrees, I will have the weight, W, bearing down at 200 pounds. Opposing this will be the normal force, which will not necessarily be equal to 200 pounds. In this case, it will not. The normal force, and then, you know what, I actually like to call it F normal, F sub n. I kind of like that one better. And then the frictional force opposing the motion. Say force of friction. I like to call it F sub Fk, force of friction kinetic. But you can choose whatever variable suits your fancy. And then here, I'm going to have my inertial force ma. Here. Let's see, here, ma. Now, ma though, let's find the mass. How might we find the mass? Well, let's think about this. Mass is going to be, we need the mass of the block though. See the difficulty of this? We are given the weight of the block, but that's a force. We need a mass. So I'm going to say that mass equals weight over g. So that's going to be 200 pounds over what? What number? Good, 32.2 feet per second squared. And that will come to 6.21 pounds second squared per foot. Isn't that a lovely unit? Could just use the metric system, but no. Okay. So now I want to do a summation of forces in the x direction. Summation of forces in the x direction is going to produce max, or just ma, I should say. I don't need a second a sub x here, simply because this thing is only going to be allowed to move in the x direction. This thing, it obviously can't go flying, digging into the ground, and it's not going to be flying through the air, so therefore the only acceleration will be one in the x direction. ma. Then so if I then go and apply this, if I look at the x component of each of these, I would have p times cosine of 30 degrees minus, here, let's see, now I actually probably should find the frictional force, great, no, find the frictional force first. So maybe I'll do that before I even do the force balance. I'd like to actually maybe nail down the frictional force if I could. So m equals w over g equals 200 pounds. Okay, and we had that before, the 6.21, so we don't have to do that again. But then, let's see this. F, okay, we know that force of friction kinetic is equal to F normal times mu kinetic. F normal times mu kinetic. So this is what I'm going to use in my summation of forces in the horizontal direction. The summation of forces in the x direction then equals ma. And this will produce then that p cosine 30 degrees minus 0.25 F sub n, normal force, equals 6.21 pounds per second squared. This is the ma. This is the m times the a, essentially. So the m, so again, this is going to equal, remember, the x is going to equal the x. The y is going to equal the y. So our m is 6.21 pound second squared per feet, or per foot. And this is multiplied by the desired acceleration, which is 10 foot per second squared. 10 feet per second squared. It's a really bad degree sign, 30 degrees. And if I do a summation of forces in the y direction, this will be negative 200 pounds minus p sine of 30 degrees minus p sine 30 degrees, and then plus Fn, and this will equal the ma, which in this case there is no acceleration, so it is simply 0. That's just a statics problem. Now I essentially have two equations and two unknowns. So I solved basically. I have p. I have everything except p and f sub n. I have two equations. I can simply solve for them, and if I do this, I will get that p is equal to the desired 151 pounds. From this point forward, once it's all set up, this is just basic algebra. There's no more unit conversion needed. It's just p cosine 30 minus 0.25 Fn, etc., etc. You know how to solve systems of equations by now. I don't know if I need to go all the way through that.
There's two equations and two unknowns, right?
Yep, there's two equations and two unknowns. See, I have the fx equation. This would be equation, let me label these, if I can write properly. This is equation 1. This is equation 2. And basically my unknowns are, well, Fn, P, Fn, and P. You go through, you have cosine of 30 is just a number, 0.25 is just a number. All of these will reduce to a number with some units, etc., etc. And you have two. It's a very simple solving a system of linear equations. It couldn't be simpler. It's fairly straightforward. Okay. So let's look at another one, maybe something a little bit more complicated. Let's look at a system of where things are joined together. A system of codependent motion, perhaps we could call it. System of dependent motion. Codependent, that's getting all sorts of problems, but anyway. Okay, so I have another example problem. And let us say that I have a flat surface and a ledge, or a ledge and a flat surface, or whatever you want to call it. And here there will be a pin, or a simple pin and a pulley. Now, hanging down from this, from the center of the pulley, will be a cord. And this will go then and wrap around another pulley, a smaller pulley, which will then come up here, wrap around, and connect to this. And there will be a pulley here, hanging from this pulley, and hanging from this will be a weight. And this weight will be 300 kilograms, so something in metric for once. 300 kilograms. And this will connect to a block which has a mass of 100 kilograms. And I will also say, so this is all given. Also, the pulleys and horizontal plane are frictionless. Pulleys and horizontal plane are frictionless. And there we have it. And the pulley is the pulley can be assumed of negligible mass. If it did not have negligible mass, then we have to consider the rotational inertia of the pulley and look into all of its rotational momentum and all that fun stuff. So, but if we can just say the pulley has negligible mass, or you can just say zero mass here. And also, let's see, so we have all that. That's what's given, and then we want to find the acceleration of the system. Or actually, the acceleration of each block. I cannot just say the acceleration of the system, it need not necessarily be the same. The acceleration of each block, and B, the tension in the string. If this were simply joined rigidly, well, not rigidly, but if this was simply joined to this one by a single string hanging off a single pulley, well, then I would only have one value of acceleration for the entire system. It would simply be a continuous string, and if this went down half a meter, this would have to go over half a meter. We can actually see here there's probably a twice relationship. If this, basically, if this moves here, if this moves by 1 meter, this is probably going to move by half a meter, right? It's the double relationship here. So this is going to probably be 1/2 of the other one, but we'll see that. So let us begin looking through this. So the very first thing I want to do is I want to define a coordinate system. And I think what I'm going to do is I'll define it like this. I'll have my blocks here and here. But then I'll have my origin here. And I'm going to define forces to the right this way as x positive and downward as y positive. So here y will be going downward. Now, so let's see. The first thing I need to do is, my first step is going to be, we do this for any kind of dependent system. Write the kinematic relationships. So my first step will be to write the kinematic relationships for any dependent motions. Oh, and also I forgot to mention that this is going to be, this one here is block A, and this here is block B. So block A has a mass of 100 kilograms, and block B has a mass of 300 kilograms. So again, A and B here. And so I know a few relationships here. One, YB is going to be equal to 1/2 XA. I know that that YB here is going to be, because of our pulley relationship, if this thing moves 1 meter, this is going to move 1/2 meter, right? There's going to be a 1/2 relationship. So if A moves 1 meter, this thing's going to move 1/2 meter, right? Because we double the distance, or we halve the distance with the two pulleys, depending on our perspective. Does that make sense to y'all? So if I pull this down by, one way to think about this, you don't actually need to do a lot of math to figure this out. If I pull this down by 1/2 meter, think about that. That means that this chord is going to increase by a length of 1/2 meter, and this chord is going to increase by a length of 1/2 meter, which means the total length here, the total change here, all of that extra length has to come from this piece here. So if this one increases by 1/2 meter and this one increases by 1/2 meter, this one has to change by an entire whole meter. So this kind of relationship always, when you have a pulley on two ropes, it's on two cords, it's always going to have half the displacement of the origination point. So YB is going to be 1/2 XA, or I could also say AB is equal to 1/2 AA. So we have these following dependent kinematic relationships. We don't need to do any balance of forces to see this. We don't need to use Newton's second law at all. Basically, we're trying to get some points on the board and figure out any fundamental relationships that will allow us to solve for these for our overall system balance. Okay, so let's.
Explain the intuition behind the AA.
It's the intuition behind the AA. It's the same kind of thing. If there is a 1/2 relationship between the displacements, there's going to be the same 1/2 relationships between the accelerations. We could actually prove that, though. If I took the derivative of this with respect to time, I would get, well, let's see. The derivative of this with respect to time, right, is going to be.
Constants will remain.
The constants are going to remain, yes. That's what it's going to come to. The constants are going to remain. Whenever I take the derivative with respect to time, I would basically get y dot is equal to 1/2 x dot. I'd get y double dot is equal to 1/2 x double dot for the A. All right, moving on. So 2, I'm going to draw some diagrams. Draw free body diagrams and kinetic diagrams. Free body diagrams and kinetic diagrams. So for block A here, I'm going to have 2 diagrams. So I'm going to have a total of 4 diagrams for this one. This will be all sorts of fun. I'm going to have for A, well, there's going to be weight, so WA, there's going to be the normal force, F normal, Fn, and the tension. Those are our, that's our thing here. And also, let's see. Well, you know what? I'm going to go ahead and say we don't know if the tensions are going to be equivalent, so I'm just going to label this as tension 1 and tension 2. Tensions. So I'm going to have tension 1 here. And then the inertial forces on this, well, all I'm going to have is pointing in the direction of motion. I'm going to have MAAA. Again, I know it's going to accelerate in this direction, so I'm going to, because if this thing is being driven by gravity, the only way that this thing can move is if this block moves to the right and block B moves downward. Now, I could actually force it to go the other direction if I pulled on this block with a great force, but they would have to tell us that force. They would have to indicate some, they could say, oh, it's moving at this acceleration to the left or something like that, and we could calculate other things. But if this thing is only moving under its own power, the only way it can move is downward for block B and to the right for block A. MAAA. And here, MA, of course, is going to be equal to our 100 kilograms. 100 kilos. Then for block, so let me just label this A. And then for B, for block B, you're going to have tension 2, and you'll have the weight 2, or weight B. And here, if I think about it, I can find this fairly easily. Weight B is just going to be the mass times the acceleration due to gravity, and this would be 2940 newtons. 2940 newtons here. And then on block 2, or on block B here, there's going to be tension 2 pulling upward. Oh, sorry, that's not on inertial diagrams. I'm confusing it with something else. My inertial force would be here. This would be MB AB. MBAB. Where the mass B, where MB is equal to 300 kilograms. And then I might have one other thing that I'm not gonna bother finding a inertial diagram for because it doesn't have a mass. We actually indicated that it doesn't have a mass. But point C here would be the pulley itself. So let me label this point here as C and make clear I'm talking about B here for the block. See, points for pulley C here, if I look at the forces on this, things are a little more complicated. This is what's going to allow me to relate T1 and T2. So if we look at this, on T1, I'm going to have two versions of this, T1 and T1, pulling up on this pulley. And then I'm going to have T2 pulling down in it. So from this, I can see that T1 is going to be 1/2 of T2, right? I can immediately see that fairly straightforward. So now, the rest is math. Okay, can I move on? You got this? Okay. So, here, let us do a series of, the rest is just a bunch of series of summation of forces on different objects, etc., etc. So the first one I might do is summation of forces in the x direction on block A is going to be equal to MAAA. And as I've mentioned again, I'm hoping you can get through this class without needing this acceleration right here. But anyway. Okay, that's okay. It's a stupid joke. Don't worry about it. Okay, so the summation of forces on here. If I look back at block A, in the extra, I'm not worrying about the y direction at all in block A, because these forces are just going to be equal and opposite. It really doesn't matter. They're equal and opposite. If there was friction, then I would need to worry about it, because I would need to find the normal force, and then I would need to find, balance that against, put that into the equation for tension, et cetera, et cetera. But because this thing is frictionless, we can just safely ignore it. And so then this would be T1 is equal to 100 kilograms times A sub A. So that will be one equation that we can use later. Then I can do the summation of forces in the y direction on, let's say, block B. On block B, that's going to be MB AB, or simply MB times G. That's going to be weight. I don't like how that looks. MB times G, that's the weight here, minus T2 is equal to MB AB. All right, and so then I can say 300 kilograms times 9.81 meters per second squared minus T2 equals 300 kilograms times AB. Or this could reduce to T2 is equal to 2940 minus 300 AB. So I have, and this is essentially, so I have one equation, T1 equals 100 AA. I have T2 equals 2940 minus 300 AB. And so then I can keep working through some of the rest of this. So then I can do a summation of forces in the y direction on object C, the pulley. This is going to be equal to MC AC. However, that will be equal simply to 0. We're not looking at the acceleration of this thing. Well, actually, we are looking at the acceleration of this thing. Sorry. The reason it's 0 is y. Why is this 0? I can neglect the MCAC term of the pulley. And it's not because the acceleration is 0. It is accelerating. Rather, I can... Yes, because the mass is 0, yes. So in any case where either, for any object, whether the acceleration is 0 or the mass is 0, it will be neglected in this side of the equation. So that's the same reason, if we actually wanted to do this truly properly, this could be if we wanted to, we could make this a devilishly complex problem. I don't know if you've thought about that. Like, think of the things we could consider if we really wanted to. We could, I don't know if you've thought about how devilishly complex you could make a problem like this, but if you wanted to, think about what you could do. We could look at, if I really want to make this a hellish problem, we won't do that here, but if we wanted to, we could say, okay, well, let's not assume the friction is 0, because it's obviously not. Let's assume that, because, there's going to be some friction, so we could model that. Each of these pulleys are going to have some amount of friction, and they're going to be different amounts of friction, and those will probably be dependent on the velocity that thing is turning. Each pulley will probably have some mass, and in turn will have some sort of rotational inertia. And don't forget, the whole thing is air resistance. We'll have to consider the air resistance of the block, the air resistance of this pulley, the air resistance of this spinning pulley in its own diameter, and the air resistance of this block here, and plus the mass of the string and the tiny air resistance of the string itself. Oh, that's even better. Yes, I love that. The elasticity of the string. Perfect. Yes, we could consider the string is not truly a rigid body, and it would be stretching a bit as forces are applied, and we could just go down this rabbit hole all day. So, but let's not do that. Let's keep it nice and simple and ideal. And even in most engineering contexts, it's very rare to ever go into something with that quite degree of complexity. Like, the only time you ever really see that kind of really insane, let's look at every single thing with no assumptions kind of thing, that's almost, what you're looking at there, yes, is almost like a NASA rocket science and things like that. That's where you need...
Situations where like a small change could have a big
Yeah, situations where every fraction of an ounce counts and you need to shave off every last bit of material to your design. That's where you actually need to consider those types of really crazy analyses. So if you love that sort of thing, maybe you could have a future at NASA. You're in the right city for it, that's for sure. Anyway, so back to this, MCAC equals 0. And then if I look at the sum of forces on here, well, if I go back to the free body diagram for the pulley at C, I can say that T2 minus 2T1 is equal to 0. Fairly straightforward. So, let's see. Well, how many unknowns do I have? I have T2, I have T1, so that's 2. I have AA and AB, so I have 4 unknowns. See the problem? See the problem with this? I have 4 unknowns and only 3 equations. Is this system just unsolvable? Should we just give up and go home?
Yes.
That is not a good attitude. No, you won't get into NASA with that attitude. Anyway.
We're going to relate the accelerations, right?
Exactly, we can relate the accelerations. Remember how the first thing we did was write these out? These are some equations we can later use. Now, in our case, the acceleration, the y equation isn't going to be very useful, but the acceleration one definitely will be. So the final step, combine force equations, or kinematic relationships with these force equations. Kinematic relations, the kinematic relationships, and they're called kinematic relationships because if you think about them, these equations, the acceleration of block A is equal to the acceleration of block is equal to 1/2 so the acceleration of block A is twice the acceleration of block B. That kind of relationship. It's kinematic. What that means is because they are physically joined together, I don't care what their exact masses are. It doesn't matter what their exact masses are, regardless of what forces or what acceleration this thing is going into, simply because of the way the pulleys are arranged, that relationship has to hold true. So I do have the YB equals 1/2 XA. Now, if I was doing like an energy type problem that I had to do a work equals force times distance or something like that, this may be useful there, but for our purposes today, that's not going to be particularly useful. But our AB is equal to 1/2 AA. This will be useful. Equals 1/2 AA. So then I can say I can look at this one. I have T1 equals 100 kilograms or 100 AA here. I already had that previously. But then I also have T2 equals 2940 minus 300 AB minus 300 AB. However, AB is equal to 1/2 AA. So then I could say this is 2940 T2 is equal to 2940, so that's just an algebra problem from here, minus 150 AA. This is by substituting in 1/2 AA for AB here. And then I also know that if so I have T1 and I have T2, and then let's look at the expression T2 minus 2T1 is equal to 0. So if I substitute in this expression for T2 and this expression for T1, suddenly I'll have an equation with only one unknown. So 2940 minus 150 AA minus 2, or minus 2 times 100 AA. All of this is equal to 0, and I can find that AA is equal to 8.40 meters per second squared. And then from this, everything else just falls into place fairly quickly. AB, you just take this and divide by 2. It's going to be 4.20 meters per second squared. T1 is going to be simply plug and chug. It's going to be 100 times AA, or 840 newtons. 840 newtons. And then T2 equals 2A or 2T1 or simply 1680 newtons. 1680 newtons. Fairly straightforward, hopefully, from there. The devil is really set. So these things, the math isn't really that complex on most of these problems. There may be some more complex ones, but the devil of this is not really in the math. The algebra really isn't that hard. The devil really is in setting them up. Setting them up, choosing your axes, setting up your equations, etc., etc. That's where the real difficulty of this is. All right, any questions on that? So again, if I look through my basic series of steps, my steps again are to first, I want to set up any basic kinematic relationships that will exist between any kind of conjoined or dependent parts, where if there's a pulley and a string and there's two objects glued together, anything like that, I know I'll have some sort of dependent motion. So I immediately write those off, write those down and get some points on the board, basically. Then I set up, for each of my objects, I set up a free body diagram and a kinetic relationships or kinetic force diagram, where I show the inertial forces on each of the blocks or in each of the objects, whatever they are. And then I continue through setting up, doing equations of Newton's second law for in the x and y direction, and then you work through it from there. All right, so any other questions on that? Hopefully that's fairly straightforward. And so I think we have time today. I think I'm going to move on to kinetics, including looking at the normal and tangential coordinates. So new topic. And then on Tuesday, we will get on to conservation of angular momentum. We have a lot to cover on Tuesday, so I did want to get to this today if I could. Because on Tuesday, we're going to have to talk about conservation of angular momentum. We're going to talk a bit about some more of Newton's laws, including gravity and orbits. And so those are going to be really fun. That would actually be the perfect day to talk about space, which I probably will do because I kind of like space. And I am a bit of a space cadet, in case you can't tell. Oh, you hope I don't space out. Oh, okay. Yeah, I've done some pretty bad ones myself. Okay. Okay, kinetics. Sorry, I try to keep things lively. I try to make sure all my lectures are very dynamic. I'm so sorry. Okay, so let us look at kinetics, normal and tangential coordinates. The normal and both in normal and tangential coordinates. So previously we've been working through analyzing these in the x and y direction. I want to analyze them in the normal and the tangential direction. So this may be an example of so this can be like a sort of forces that you can sort of have for curvilinear motion, and some examples of this. Anyone here from a military background by any chance? Oh, are you okay? I don't know if anyone has. So maybe not. I guess I was going to ask if anyone had been in a fighter jet before, but that would be. I guess I didn't get quite so lucky this time. Has anyone ever been on a roller coaster? I should see more hands than one. Come on, I've all been on roller coasters, or a lot of us at least. Many of us have been on roller coasters, right? And so if I look at inertial forces, if I'm looking at tangential forces and things like that. Fighter jets and roller coasters are both things that are capable of generating a great degree of, say, normal accelerations. If you look at, or normal inertial forces, that kind of thing. So if you have a roller coaster, we go to the top of the hill and then we come down. And we go down to the bottom of a really large hill, or go through a loop, etc. That kind of thing. Or the worst case scenario is, actually, did anyone ever play Roller Coaster Tycoon growing up? I love that game. That was especially because it calculated the accelerations for you by itself. It was great. Although I probably shouldn't be allowed to design roller coasters in real life like I did in that game, because what I always love to do is I love to take the roller coaster to the highest peak, have it come down the highest height you could build, have it fall down a straight vertical drop, And then immediately, if I'm looking down from above, so this is in elevation view, and then if I look at from, so this is elevation view, and then in plan view, so if this is the roller coaster coming down like this, once it reaches the bottom, it just immediately makes a sharp, unbanked right turn. I'm no expert in biomechanics, but I'm pretty sure everyone on that ride would be very quickly dead. Yes, because normally when you take turns like that, well, it would be kind of like, imagine you were in an automobile. Like, think of the radius of curves on a small suburban side street, the kind of street most of you probably live on, like where you have, it's like it's kind of a suburbs with single-story houses, single two-story houses, that kind of neighborhood. And where two side streets meet, you have just kind of like you do have some curve in the curve, but it's a very sort of, it's something you can go around at 20, 30 miles, even 30 miles an hour is way too much, 15, 20 miles an hour max, And then compare that to the highway. Compare that to the interstate where you're going 75, and the curve is this, this curve it might have a radius of curvature measured in miles, and it is, or at least thousands of feet, and it's banked too to ease the forces. And so imagine if you're going 80 miles an hour, and somehow you'd have to like bolt your car down to keep from flipping or something, but you have to put it almost on a track to make it do this. But let's say you could somehow force your car to go around the suburban side street corner at 80 miles an hour. That would not be a good day for you or your car. It would probably break both of them. One worse than the other, and let me just say the car is not going to be the one losing. But anyway, these are these are what we call normal forces. Normal forces are what we might call centripetal forces. So you've probably heard the term centripetal force. Centripetal means center seeking, right? So when we say a centripetal force or a normal force, we're looking at forces toward the center of curvature. And if you remember in high school, uniform circular motion, no, this isn't uniform circular motion. We're far beyond the level where we look at purely uniform circular motion, but we can, we'll look at some more general cases of it. So let's consider this. Newton's second law, again, of course, is, so let's look at equations of motion. Newton's second law, of course, is the sum of forces is equal to mass times acceleration. Sum of forces is equal to mass times acceleration here. Now, I could have, say I have a curve. Actually, I kind of like doing the purple path, so I'll do that. If I have a path, an arc or something like that, there's an object traveling along an arc. We looked at this previously, but we previously ignored the, we just said it had a, we were ignoring the mass, we simply said it had an acceleration. Now we're going to consider the forces on this object. So I'm going to have two forces on this object. I'm going to have both the n and the t direction. So in fact, let me label my axes first. I'm going to have a tangential axis here. This would be the tangential axis t. And I would have the normal axis n. So the tangential and the normal axis, and these are at right angles to each other. The tangential axis is basically the tangent line pointing in the direction of the velocity at one instant, and the normal is perpendicular to that. It is pointing toward the center of motion. And then along each of those, I could have two summation of forces. I would have the summation of forces along the tangential direction, summation of forces along the tangential direction, and I would have the summation of forces along the normal direction. So what we see here is that instead of just looking at forces in the x and y direction, we can actually use a different coordinate system, this time a rotating coordinate system or a changing coordinate system that is looking at the normal and tangential directions instead of simply the global x and global y directions. So it's just a different way of representing our coordinate systems. So for tangential and normal components, for tangential and normal components, Well, the sum of the forces in the tangential direction is going to be equal to the mass times the acceleration in the tangential direction, and the summation of forces in the tangential direction in turn is going to be equal to m dv dt. The acceleration in the tangential direction, I cannot talk, but all right. This is going to be equal to the change in velocity with respect to time. And then this is that we saw last time, that we saw the relationship between tangential acceleration and velocity. The tangential acceleration is going to be equal to the derivative with respect to time of the velocity. Meanwhile, in the normal direction here, the summation of forces in the normal direction would be equal to m an, which I could also replace an with v squared over rho. Summation of forces in the normal direction is equal to m times v squared over rho. And so this would be something like a free body diagram in a rotational system, and this would be something like a kinetic diagram here. I'll draw it down here. It would be something like this, where we have our curving, I want to do that in purple, where we have our curving path here, and a mass here. Green masses are happy masses. Then our coordinate system are t and our n, and we would have inertial components or inertial forces here as well. I would have mat, and I would have man. Now, if you look back to high school physics, even on this problem and in previous problems, you may have seen some echoes. You may have seen some echoes where you're like, oh wait, I remember doing something like that. And in a way, it actually is. A lot of this stuff is a somewhat echo of some of the things you saw in even grade school physics there, high school physics. But what we're doing is, when you deal in high school, or when you're in a high school class, for instance, you usually don't talk about inertial forces. And the reason is you tend to just look at the objects and maybe do a very basic free body diagram, but you tend to try to just tease out the relationships in a manner that is not necessarily as rigorous and mathematically involved. So the benefit of that is that the math is simpler, so it's easier for young students to do, but the downside is that it's not as rigorous, which means if your system gets much more complex than this, the high school methods start to break down very quickly, where you're just trying to look at things and see how they balance out and say, okay, this force balances with this one, this kind of thing. But when you actually but the inertial forces become very useful when you start dealing with much more complex systems. So that's why we're going to the trouble of doing the full balance of forces and the full inertial diagrams, etc., etc. I know it may seem tedious, but the whole idea is to produce a system that works in, produce a method that works in multiple complex systems. Okay, so I think next I might work through a problem involving, let's do something involving a pendulum. All right, so let's do another example. And all of this is given. I'm going to have a pendulum here. And this pendulum is supported by a point here. And it's going to rotate along. It has mass m. And we'll go ahead and assume that this thing is weightless cord, ideal pendulum, that kind of thing. This thing has a length of 2 meters. And it moves in a circle in a vertical plane. So it's going to go back and forth and back and forth and back and forth. Now, at the position shown, so the position shown is, I've also been told the angle here, 30 degrees, here. And I'm also told at this position the tension in the cord is 2.5 times the weight. 2.5 times the weight. I am not given the mass of the pendulum. The weight of the pendulum bob. Of the pendulum bob. Okay, and I wish to find, so all this is given, and find the velocity and acceleration of the pendulum in this position. And acceleration of the pendulum in this position. All right, so we're going to go and I'm going to create both inertial and free body diagrams for this problem. Okay? Both inertial and free body diagrams for this problem. Now, so the first thing I'm going to do is the free body diagram. And I will have to define a system, or a coordinate system. And so I'm going to say I'm going to have the n direction, which is going to point toward the center. The n direction, which will point toward the center. And then the t direction, which will point downward. Now, the question might be, why would I put the t pointing this way rather than pointing this way? Well, I've decided I want my acceleration to be positive. So what I want to do is I want my acceleration to be positive here. And so if whenever the plumb bob is here, what is producing the acceleration is gravity. So as it flies upward, the acceleration is going to actually be pointing downward, won't it? Because gravity is always going to pull downward. So I'm just decided that I want my acceleration to be positive, so that's why I'm putting my t direction there. Because my acceleration will be like this. But anyway, let's take a look at this. Let us look at the forces here. There are going to be two forces on here. There's going to be weight, which is equal to mg. And this is not in the normal or tangential direction. And then I'm going to have tension, which will be directly along the normal direction. So this is going to be tension equals 2.5 mg. Then if I do a kinetic diagram, I wish to also do a kinetic diagram. A kinetic diagram and I will simply have MAT and MAN. MAT and M, actually that shouldn't be a subscript, M times AT and M times AN. We have mat and man. All right, so let's do this. So I'm going to do a summation of forces. So let's just work through the summation of forces. If I do a summation of forces in the tangent direction, so the summation of forces in the tangent direction, well, I will get that in the tangent direction here, I get mg times the sine of 30 times the sine of 30 degrees equals MAT. Oh, look at that. This is why they didn't give us the mass, because it's going to cancel out. That cancels out. And so AT then, so that leads to AT equals G sine 30 degrees. And that equals 1/2 times G, or simply 4.9 meters per second squared. 4.9 meters per second squared. The summation of forces in the normal direction equals the summation of forces in the normal direction is going to be equal to MA, but this is going to be equal to 2.5 mg. That's the summation in the normal direction. 2.5 mg, that's this force here, mg minus mg cosine theta, and this equals MAN. And the masses again cancel out, not surprisingly. That goes away. And that looks too much like a 2, AN. And AN then equals equals G times 2.5 minus cosine 30. Or simply, so that's our first answer here. Our AT is 4.9 meters per second squared. And here AN is equal to 16.03 meters per second squared. Meters per second squared. And then to get the velocity, AN equals VP over rho, or sorry, V squared over rho. So then V equals equals plus or minus the square root of AN times rho, or plus or minus the square root of 2 times AN, or just AN 16.03 times rho, which is 2 meters, or plus or minus 5.66 meters per second. And I do not reject either of those as non-physical, because the same acceleration will result regardless of how this thing is moving. If this thing is going upward, then the acceleration will be downward. If it's going so basically, regardless of which direction velocity is, the acceleration will be in the same direction. Yes.
Why is that for the normal force?
Uh-huh.
Why is the cosine negative? Is it because of the position of the tangential force?
Let's see. Why is the cosine negative?
Yeah.
Because this is look here. So this refers to mg as weight, and so it's the negative. Basically, weight will have a tangential and a normal component, but its tangential component will be positive, but its normal component will be negative because it's pointing opposite my normal axis. Does that kind of make sense? Okay. All right. Any other questions? Okay. Well, I think I'm going to let you go for today. I think we got a lot done. So I'll see you all on Tuesday. Watch out for the homework be on the lookout. Don't watch out for it. Be on the lookout for the homework for the coming week on, I'll post that probably tomorrow. That'll do it. And as always, thank you.